Today, I'll be talking about halogenation of alkanes. Alkanes are hydrocarbons and they are known to be very inert. However, they do undergo reaction with halogens via a free radical mechanism. So, a long time ago, scientists took methane and heated it at very high temperature, and they observed no reaction. They also exposed it to UV light, and there was no reaction, and hence alkanes were considered to be inert. However, when chlorine molecule was heated or subjected to UV light, chlorine atoms were formed. We can see here these fish hook arrows are representative that a homolytic fission is taking place and the bonded pair of electrons is broken so that each atom takes one electron, and so we get two chlorine atoms from one molecule of chlorine. When methane was mixed with chlorine gas and heated or treated with UV light, two products were observed: methyl chloride and hydrogen chloride. So scientists wanted to see if other alkanes also behave in the same way. So they took propane and mixed it with bromine and heated it, and they've got again two compounds. This is an alkyl bromide and this is hydrogen bromide. And they were surprised to see that they got about 95% of 2-bromopropane. They were surprised because there are 3 hydrogens here and 3 hydrogens here, so 6 primary hydrogens and only 2 secondary hydrogens. But bromine looked like it was very selective in replacing only secondary hydrogens. So they checked it out with tertiary butane. So tertiary butane also reacts with bromine in presence of UV light to give tertiary butyl bromide and hydrogen bromide. In this case, the selectivity was very high and they got 99% of 2-bromo to methyl propane. And this hydrogen is a tertiary hydrogen. So I've made a model of tertiary butane right here. You can see you have the 3 methyl groups, 1, 2, 3 methyl groups right here, and then this is the hydrogen. So this hydrogen is pretty sterically hindered, but even though it's sterically hindered, this was the only hydrogen that was kind of replaced by bromine. Bromine to give you the T-butyl bromide. Okay, so this is 2-bromo, 2-methyl propane. Okay, so this atom is the bromine. This is the carbon-bromine bond. So the scientist figured that based on the experimental observations, the reaction of halogens with alkanes probably proceeds via a free radical mechanism. So this is a drawing of methyl radical and this is the model. I prepared a model right here. You can see this is the carbon atom in the center. These are the 3 hydrogens, 1, 2, 3 hydrogens, and this blue is the p orbital. This is the p orbital. Okay, the methyl radical, all the 3 hydrogens are in the same plane, and the bond angle is 120 degrees. So the methyl radical is trigonal planar, and the p orbital is perpendicular to the CH bonds. Okay, it's perpendicular to the CH bonds, and the p orbital has a single electron. So radicals are nothing but they're composed of more than one atoms with a single electron in the p orbital. So the 3-step mechanism, let's look at the 3-step mechanism for radical chain reaction. Why is it called a chain reaction? It's because the propagation step can continue forever. So the initiation step is the bromine molecule will undergo a homolytic cleavage and to form 2 bromine atoms in presence of UV light or when heated above 200 to 300 degrees centigrade. The next step is the propagation step. In propagation step, the bromine atom will abstract the tertiary hydrogen from tertiary butane to give you the T-butyl radical, which and also form hydrogen bromide. The T-butyl radical will further react with bromine molecule to give you the product, and the bromine atom is regenerated. These steps are called the propagation steps. The last sequence of steps is the termination steps. So the way the reaction can be terminated is the 2 bromine atoms combine to form the bromine molecule, or the T-butyl radical reacts with the bromine atom to give you the product, or 2 T-butyl radicals combine to give you the product. So radicals are composed of more than 1 atoms, and this is the fish hook arrow that is representative of the homolytic fission. So in order to understand why you get 99% and very high selectivity of the tertiary hydrogens being selected over the secondary, over the methyl, we need to understand the stability of the radicals. So here I have the different radicals: methyl radical, ethyl, isopropyl, and T-butyl radical, and we'll try to understand why bromine atom selectively picks only the tertiary hydrogens. So this is the bond line structure of methyl radical, ethyl radical, isopropyl, and T-butyl. And the red, so the dots are the single electron on the carbon p orbital, and the red CH bond is parallel to the p orbital. So let me explain a concept called hyperconjugation. So let's look at this methyl radical. So this is a methyl radical. It has only 1 carbon atom, and so it does not have any CH bonds that are parallel to the p orbital. The blue is the p orbital. But now let's look at if in case of ethyl radical, I'm just making a model right now. Okay, so this is an ethyl radical. This is 1 carbon atom which has the p orbital single electron, and this is the another carbon atom. So this is the ethyl radical, and you can see in this particular structure that this CH bond right here is parallel to the p orbital, and because it's parallel, it can overlap, and this is called hyperconjugation. So when parallel CH bond electrons overlap with the p orbital with a single electron, it results in stabilization of the radical. Let's look at isopropyl radical. So this is isopropyl radical, 1, 2, 3, 3 carbon atoms. This is the p orbital with the single electron. And in this case, what you can see here is you can see that there are two hydrogens which are near parallel to the p orbital. So this is the p orbital, and these are the two hydrogens which are almost parallel, and then they will overlap with the p orbital to give more hyperconjugation. So in this case, there are two CH bonds. Let's look at the tertiary butyl radical. So this is a tertiary butyl radical. So this is the central carbon which has the p orbital, and then we have the three methyl groups, 1, 2, 3. So three methyl groups. And for this particular case, we have three CH bonds, 1, 2, 3, 1, 2, 3, three CH bonds that are near parallel to the p orbital, and that for that reason the hyperconjugation is much more better for the t-butyl radical as compared to the isopropyl radical. So for that reason, the t-butyl radical is the most stable, and the stability of radical increases as we move from methyl to t-butyl radical due to hyperconjugation. Another concept I want to cover here is that let's look at another different kinds of radical. This is allylic radical. You can see electron on this particular carbon atom right here next to the double bond, and it can go into resonance with the double bond. It also has a CH bond which is near parallel, so it can also undergo hyperconjugation. So this is an example where it can undergo resonance plus hyperconjugation. So it's going to be more stable than or at least as stable as the t-butyl radical. And then this is the benzylic radical. Benzylic radical is very stable because the single electron on the carbon atom can delocalize into the ring. So whenever radicals can enter into resonance, then they are more stable as compared to hyperconjugation. So let's look at the reactivity of halogens in abstraction of the CH bond or CH bond of alkane. So what scientists have found that is iodine is almost not reactive at all under all conditions, whereas fluorine is the most reactive halogen. Chlorine and bromine are of intermediate reactivity. So in this table, what I have is the type of alkane bond. It can be a primary alkane bond, the CH bond, and this carbon atom is the primary carbon atom, and then this carbon is the secondary because it's attached to two alkyl group. And then we have, this is the tertiary hydrogen because it's attached to a tertiary carbon. And then in this row shows the reactivity, relative reactivity of bromine. You can see as you move from primary to tertiary, the relative reactivity increases by a lot. In case of chlorine, the difference from primary to secondary is, quite a bit, but moving from secondary to tertiary is not so much. And because of the big difference in selectivity by bromine, Bromine is used in organic synthesis due to its moderate reactivity as well as its excellent selectivity for tertiary hydrogens. So you may be aware that Freon, which is a refrigerant, undergoes free radical reaction and it destroys the ozone layer in the atmosphere. So how does that, how does it do it? So let's look at the mechanism. So the first step is the initiation step. So Freon, this is Freon, in presence of UV light from sunlight, it will break, it will undergo homolytic cleavage and it will give rise to the chlorine atom. This chlorine atom is responsible for destroying the ozone layer by the following propagation steps. So the ozone in the atmosphere reacts with the chlorine atoms, which further then reacts with the oxygen to regenerate the chlorine atoms. So chlorine atom is regenerated and this goes on till all of ozone layer is depleted. So why is that harmful? Well, ozone blocks 99% of the UV light that's harmful for life. So ozone prevents UV light from reaching the surface of the earth. So ozone in presence of UV light will give you the oxygen atom and oxygen. This is what ozone does, and it helps people. So in summary, radicals are formed by homolytic cleavage, and each bonded atom takes one shared electron, shown as a fishhook arrow. A radical is composed of more than one atom. They are very reactive and cannot be isolated. Alkyl radical has a single electron in the p orbital of the carbon atom, and that carbon atom is trigonal and planar. Radicals can be stabilized by hyperconjugation or by resonance. And bromine is very selective and hence used in organic synthesis to prepare alkyl bromides. Thanks for watching and have a nice day. Like and subscribe.